Two birds are flying towards their nest, which is in a tree. Relative to a fixed origin, the flight path of each bird is modelled by a straight line. In the model, the equation for the flight path of the first bird is R1 is -152 plus lambda 2a0, and the equation for the flight path of the second bird is R2 is 4 -13 plus mu 0 1 -1, where lambda and mu are scalar parameters and a is a constant. In the model, the angle between the bird's flight paths is 120 degrees. Determine the value of a. So what we're going to be using here is that a dot b is mod a, mod b cos theta, where theta is the angle between the two vectors. Now here we have 2a0 dot 0, 1, -1 for the dot product. And then the magnitude of a. Remember, we are only looking at the directions here. So that is going to be the square root of 2 squared plus a squared. And then we'll have the square root of 1 squared plus 1 squared. And then we have the cosine of 120 degrees. This side gives me a, so I have a is root 4 plus a squared root 2 times -1/2. So I have -2a is the square root of 8 plus 2a squared, if we put the two square roots together. Squaring both sides gives me 4a squared is equal to 8 plus 2a squared. 2a squared is equal then to 8. So a squared is equal to 4 and a is positive or -2. But if we go back to this line where we have a negative equal to a positive, that tells us that a must be equal to -2. Let's call that 1. A is equal to -2 from 1. Now that we have that, we can update this vector here as 2, -2, 0. Verify that, according to the model, there is a common point on the flight paths of the two birds and find the coordinates of this common point. So, we're going to need the x-coordinates to be the same. So we would have -1 plus 2 lambda is equal to 4. Let's call that equation 1. And then we would have 5 minus 2 lambda is equal to -1 plus mu. Let's call that 2. And then we would have 2 is equal to 3 take away mu. Let's call that 3. Equation 1 would give us 2 lambda equals 5, so lambda equals 5 over 2. Equation 3 would give us that mu is equal to 1. 3 take away 1 is equal to 2. We need to check in 2 to make sure that works. So if we look at the left-hand side, that'll be 5 take away twice 5 over 2, which is equal to 0. If we look at the right-hand side, that would give us -1 plus 1, which is equal to 0. So that works. So we now know that they intersect. We've checked that. And then we just need to find the point, which we can do by putting mu equals 1 in here, or we could put lambda is equal to 5 over 2 up here, but I'm going to work with the 1. So that is going to be 4, because it's just 4 plus 0. And then we've got -1 plus mu, which is 0, which we knew from our check before. And then we've got 3 take away 1, which is 2. So 4, 0, 2. The position of the nest is modelled as being this common point. So the nest is at 402. The tree containing the nest is in a park. The ground level of the park is modelled by the plane with the equation 2x minus 3y plus z equals 2. We want to determine the shortest distance from the nest to the ground level of the park. In other words, if this is the park and this is the nest, we want this distance. Now you can certainly do that with projections and one thing and another. I have a method that I like to use, however, which is I'm going to construct a parallel plane that contains this point just here. So if it's a parallel plane, it will have the same left-hand side, but that was going to be equal to a different constant than 2. So we can then use the point to work out the constant. So it's going to be 8 take away 0 plus 2 is equal to 10. So the plane parallel to the park, the ground, is going to be 2x minus 3y plus z is equal to 10. Now what we're utilising here is the fact that the constant here and here are related to the distance of the plane from the origin. So the way that it is related is that that constant, let's call it constant, divided by the magnitude of the normal is equal to the distance. So distance 1 is going to be 2 divided by the square root of 2 squared plus 3 squared plus 1 squared, so that's root 14. And the second distance is going to be 10 over root 14. The fact that they're both positive tells us that the planes are the same side as the origin, and therefore the distance between them is going to be 10 over root 14, take away 2 over root 14, and that is going to give us 8 over root 14, which is 8 root 14 on 14, which is 4 root 14 on 7. We just have one part of the question left, which is this one here. By considering the model, comment on whether your answer to part C is reliable, giving a reason for your answer. There's lots of reasons we can give here. This is just 1 mark, so we probably only have to give 1, but I'll give you 3. Birds almost certainly don't fly in a straight line, so modelling them with the vector equation that we did is probably not reliable. The ground is unlikely to be a flat, smooth plane, so modelling the park as a flat, smooth plane is probably unreliable. And the nest itself is not just a point.